Introduction to Thermodynamics. Learning outcome. When you complete this chapter, you will be able to explain the principles of thermodynamics, including the laws of thermodynamics and the modes of heat transfer. Learning objectives. Here is what you will be able to do when you complete each objective. Describe the laws of thermodynamics. Explain the different temperature scales used in thermodynamics. Define heat and specific heat and perform sensible heat calculations. Describe the expansion of solids and liquids. Describe the three modes of heat transfer. Introduction. Thermodynamics is the branch of science which deals with the transfer of heat to other forms of energy such as mechanical, electrical, and chemical energy, as well as the transfer of energy from those forms to heat. The efficient use and transfer of heat energy is very important in the field of power engineering. Examples of transfers of heat which an operator must be familiar with are the conversion of heat from a burning fuel source to water and steam in a boiler, the combination of fuel and air in an internal combustion engine which drives a piston, and the extraction of heat from a refrigeration system. To understand energy conversion, it is necessary to understand the concepts of temperature, heat, expansion of liquids and solids, pressures, the general laws of thermodynamics, and certain other topics which are fundamental to the study of thermodynamics. Definitions. The following definitions are for terms used throughout this chapter. Absolute pressure, a pressure measure in which the zero mark is a measure of a perfect vacuum. It is the sum of a gauge pressure plus atmospheric pressure. The units used to represent this are kilopascals, absolute, or PSIA, pounds per square inch, absolute. Absolute zero, the temperature of an object completely devoid of any heat energy, equal to 0 Kelvin and negative 273 Celsius. Atmospheric pressure, the pressure exerted by the Earth's atmosphere, essentially, the weight of all the air directly above a measured area. Measured in SI units, kilopascals, millimeters of mercury, or meters of water. In imperial units, PSI, or pounds per square inch, inches of mercury, or feet of water. The standard atmospheric pressure is 101.325 kilopascals, 760 millimeters mercury, and 10.33 meters of water. In imperial units, it's 14.696 psi, 29.92 inches of mercury, and 33.39 feet of water. Change of state. A change of physical state between gas, liquid, or solid. Conduction. The movement of heat from a hot body to a cold one, which it is in direct contact with. Convection. The transfer of heat caused by the movement of a fluid, gas, or liquid, set into motion due to the difference in heat, and hence density, between different areas in the same volume of gas. Cooling. The process of removing heat from a substance, resulting in a decrease in temperature, or a change in its state. Density. The mass per unit volume of a substance, expressed as kilograms per meters cubed, or pounds per feet cubed. Enthalpy, or heat content. Enthalpy is defined as thermodynamic potential. For the purposes of this chapter, it can be seen simply as the amount of heat contained in a substance, relative to a base temperature that is defined to be 0 degrees Celsius. For example, considering water at 0 degrees Celsius as your baseline, the enthalpy of a mass of steam at 150 degrees Celsius would be the sum of the heat required to heat the water from 0 degrees Celsius to 100 degrees Celsius, the heat needed to convert the water to steam, and the heat required to raise the resulting steam to 150 degrees Celsius. When dealing with refrigerants, negative 40 degrees Celsius, or negative 40 degrees Fahrenheit, which is the same thing, or absolute zero are commonly used as the baseline instead of 0 degrees Celsius. Gauge pressure. The pressure of a closed system over atmospheric pressure, expressed as kilopascals gauge or PSIG. For example, if a pressure gauge on a pipe reads 50 psi, the absolute pressure of the fluid inside the pipe is 50 psi plus the atmospheric pressure, which is typically around 14.7 psi. Heat, a form of energy which, when applied to a body or substance, will raise the internal energy of that substance or body. Heating, the process of increasing the internal energy of a body or substance, resulting in its increase in temperature or a change in state. Heat transmission, the movement of heat. Heat always travels from a warmer substance to a colder substance. Latent heat, heat which changes the state of a substance, but not the temperature. For example, the heat required to change water at 100 Celsius to steam at 100 Celsius. Latent heat of evaporation, the amount of heat required to change a unit mass of a substance from liquid to a gas without changing its temperature. Latent heat of fusion, the amount of heat required to change a unit mass of a substance from solid to liquid without changing its temperature. Pressure, force per unit area. The unit of pressure in the SI system is the Pascal, which equals 1 Newton over a meter squared. It is the force of 1 Newton acting uniformly over an area of 1 square meter. Since the Pascal is a very small unit, the kilopascal is commonly used to express pressure. In the imperial system, the unit of pressure is the pound per square inch, psi, written as 1 lb over a square inch. 1 psi is equal to 6.895 kilopascals. Radiation, the method of raising the internal temperature of a substance by electromagnetic waves, for example, sunlight. Saturated steam, steam which is fully saturated with latent heat, leaving no water molecules in it, also referred to as dry steam. Saturation temperature, or boiling point, the temperature at which a liquid will, if given any additional heat energy, change its state into a gas. Sensible heat, heat which changes the temperature without changing its state. Specific heat, the amount of heat required to raise a unit mass 1 degrees Celsius. The specific heat of water is 4.18 joules per gram. Specific volume, the volume of a unit mass of a substance, measured in meters cubed per kilogram, or cubic feet per pound. The specific volume of a gas will depend on its temperature and pressure. Superheat, the amount of heat in a gas beyond what's needed for it to exist in a gaseous state. For example, steam at 150 degrees Celsius has 50 degrees Celsius of superheat. Temperature, the measure of intensity of heat or hotness of an object. Unit of heat energy, the unit used to measure heat energy, the joule or kilojoule in the SI system, and the British thermal unit, BTU, in the imperial system. It takes approximately 1 kilojoule to raise the temperature of 1 cubic meter of air 1 degree Celsius at standard atmospheric pressure. It takes 1 BTU to raise the temperature of 1 pound of water 1 degrees Fahrenheit. 1 kilojoule is equal to 0.9478 BTU. Vacuum, a reduction in pressure below atmospheric, measured in millimeters mercury or in inches of mercury. On a particular day, if the pressure is 760 millimeters of mercury, a perfect vacuum would be 760 millimeters of mercury of vacuum. Wet steam, steam which does not have the full quantity of latent heat, having some water present in it. Laws of thermodynamics. There are 2 laws of thermodynamics which we will concern ourselves with in this lecture. The first law of thermodynamics. This is the thermodynamic interpretation of the law of conservation of energy. It states that the total energy of an isolated system is constant. Energy can be transformed from one form to another, but can never be created or destroyed. First law of thermodynamics states that heat and work are mutually convertible. This law can be stated in the general form: work equals heat. In practice, only part of the heat is turned into work, or only part of the work generates heat. For example, in the expansion of a gas in a cylinder causing a piston to move, the heat supplied moves the piston and also increases the temperature of the gas, so that heat supplied is equal to the increase in internal energy plus the work done. Q equals delta U plus work done. The second law of thermodynamics. The second law of thermodynamics states that, unaided, heat will only flow from a hot substance to a colder substance. If it is required to transfer heat from a cold substance to a hot substance, such as in refrigeration, then external work must be applied. Temperature. Temperature is a measure of the speed of the molecules in a body. Increasing temperature causes the molecules to move about faster, and decreasing the temperature decreases molecular velocity. Heat will transfer from a higher temperature object to a lower temperature object in direct contact by interactions between the high-speed molecules of the first hitting into the slower ones of the second, imparting some of their speed upon them, losing energy, temperature, themselves in the process. Heat is a measure of the quantity of internal vibrational energy in a substance. Temperature is a measure of the intensity or hotness of heat in a body. For example, a large pool of water at 20 degrees Celsius has much more heat, although it is a lower temperature, than a small metal rivet glowing red hot at 500 degrees Celsius. There are 4 temperature scales which the power engineer should be familiar with. The Celsius scale is the most common temperature metric used outside of the US. It is notably configured such that the temperature ice melts at is set to 0 degrees Celsius, and boiling water is 100 degrees Celsius, with 100 evenly spaced degrees between them. Each degree of Celsius is roughly the size of 1.8 degrees Fahrenheit. The Kelvin is the SI measure of temperature used commonly in science and engineering. Its degrees are the same size as the Celsius scales. However, 0 is set to absolute 0, which is negative 273.15 degrees Celsius. So, ice melts at 273.15 degrees Kelvin, and water boils at 373.15 degrees Kelvin. The Fahrenheit is a temperature scale used commonly in America. The temperature ice melts at is 32 degrees Fahrenheit, and water boils at 212 degrees Fahrenheit. The size of each demarcation on the Fahrenheit scale is smaller than each notch on the Celsius scale. Specifically, each degree Fahrenheit is roughly 0.55 degrees Celsius. The Rankine scale is analogous to Fahrenheit as Kelvin is to Celsius. Rankine begins at absolute 0 being 0 degrees R, and each unit is the same size as the units of the Fahrenheit scale. Ice melts at 492 degrees on the Rankine scale, and water boils at 672 degrees Rankine. The Rankine scale is by far the least commonly used of these 4 scales. Measuring temperature. Liquid in glass thermometers. These thermometers are filled with mercury or alcohol, substances which will expand or contract by large amounts when heated or cooled. They are slow acting and take several moments to several minutes to adjust to a new temperature they are immersed into, although they are quite accurate, with the precision of 1 degree, and remain so for many years of use. Bimetal thermometers. These thermometers work by attaching 2 different metals against each other lengthwise. The metals have different coefficients of linear expansion, so that when they heat or cool, one strip of metal grows or shrinks more than the other, causing both of them to bend or straighten, since they are rigidly affixed to each other. Pyrometers. These devices are temperature measuring instruments which can handle temperatures higher than liquid glass and bimetal thermometers. There are various types. Two common ones, which we shall look at here, are the thermoelectric and the optical pyrometers. Thermoelectric pyrometers. These meters make use of the thermoelectric effect, the direct conversion of temperature differences to electric voltage or vice versa. By use of a thermocouple, an electrical voltage is produced which has been measured to be proportional to a temperature, so that one can determine the other. A thermocouple consists of two wires, each made of a different metal. The two wires are joined together at each of their ends, and if one of the joints is at a higher temperature than the other, a voltage is produced in the wires. Because every type of metal, and hence wire, has a different Seebeck effect, not discussed in this video. The high temperature joint is called the hot junction. Optical pyrometers. These devices work by having the operator point them at a heat source and looking through it. Inside, there is a filament which can be variably heated by an electric current. A filter is used so that a small band of color can be seen, and the current is adjusted until the brightness of the filament and the source behind it appear the same to the operator. Since it is known how much current was required to get the filament to a particular brightness, it will have been calibrated to map that to a corresponding temperature, to which the temperature of the filament and the heat source being measured will be the same. Here's a diagram of the optical pyrometer. It's worth noting that the optical pyrometer will not be seen very much in the field. It's pretty much an archaic device now, although it is covered in the material, so that's why I mention it here. The optical pyrometers have been mostly replaced by infrared pyrometers. Heat. The SI metric measurement of heat is the joule. 1 joule is the equivalent to applying a force of 1 Newton over a distance of 1 meter, a power of 1 watt over a time of 1 second, the amount of energy applied to a pivot point when 1 Newton of force is applied at a direction of 1 meter. When used to express torque like this, a joule is typically referred to as a Newton meter. The imperial system's measurement for heat is the British thermal unit. A BTU is the amount of heat needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. 1 BTU is equal to 1055.06 joules. Specific heat. Different substances can absorb differing amounts of heat before their temperature raises. The specific heat of a substance is the amount of heat energy needed to raise a unit mass of it by 1 degree. A couple of examples. Fresh water, which absorbs a lot of heat to raise its temperature, has a specific heat of 4.2 kilojoules per kilogram per degree Celsius, meaning that it takes 4,200 joules to raise 1 kilogram of water by 1 degree Celsius. Brass, whose temperature raises very rapidly with little heat energy, has a specific heat of 0.394 kilojoules per kilogram per degree Celsius. In the imperial system, specific heat is the number of BTUs needed to raise 1 pound of that substance by 1 degree Fahrenheit. Heat quantities. As may have been gathered by now, there is a direct relationship between the quantity of heat absorbed by a substance, its temperature rise, the mass of the substance, and its specific heat, which can be expressed as a formula to find any one missing component. Q equals mc times T2 minus T1, where Q is the heat absorbed by the substance in kilojoules, m is the mass of the substance in kilograms, C is the specific heat of the substance in kilojoules per kilogram per degree Celsius, T1 is the temperature of the substance before heating, either in Celsius or Kelvin, T2 equals the temperature of the substance after heating, again either in Celsius or Kelvin, but T1 and T2 have to be the same units. Example 1. Find the quantity of heat required to raise the temperature of 1 liter of fresh water from 20 degrees Celsius to 80 degrees Celsius if the specific heat of fresh water is 4.2 kilojoules per kilogram per degree Celsius. Assume that 1 liter of fresh water has a mass of 1 kilogram. Q equals mc times T2 minus T1 equals 1 kilogram times 4.2 kilojoules per kilogram Celsius times the ending 80 degrees Celsius minus the beginning 20 degrees Celsius. So the kilograms cancel out, and that leaves us with 4.2 kilojoules per degree Celsius times 60 degrees Celsius. The Celsius degrees cancel out, and we're left with 252 kilojoules. It takes 252 kilojoules of heat to raise 1 kilogram of water by 1 degree Celsius. Example 2. Find the quantity of heat required to raise the temperature of 1 kilogram of copper from 20 degrees Celsius to 80 degrees Celsius if the specific heat of copper is 0.39 kilojoules per kilogram per degree Celsius. Q equals mc times T2 minus T1. This gives us 1 kilogram times 0.39 kilojoules per kilograms degree Celsius times 80 Celsius minus 20 Celsius. Kilograms cancel out. This gives us 0.39 kilojoules per degree Celsius times 60 degrees Celsius, leaving us with 23.4 kilojoules. So it only takes 23.4 kilojoules of heat to raise 1 kilogram of copper by 1 degree Celsius. Important note: when using the formula Q equals mc times T2 minus T1, the substance cannot change state. The temperature range of T2 and T1 cannot be at temperatures in which the substance exists in two different states. So, for instance, you could not use this formula by itself to find out the heat needed to raise ice at negative 10 degrees Celsius to water at 40 degrees Celsius, because heat is required to change the ice at 0 degrees Celsius to water at 0 degrees Celsius. Linear expansion of solids. Most solids expand when heated and contract when cooled. When a pipe or rod is heated, it will increase in length in proportion to its length and to the amount of temperature increase. The amount of change per unit length per degree rise in temperature is referred to as that substance's coefficient of linear expansion. Expressed as a formula, change of length equals original length times coefficient of linear expansion times the rise in temperature. Example 3. What is the increase in length of a steel bar 10 meters long if its temperature is increased from 20 degrees Celsius to 70 degrees Celsius? The coefficient of linear expansion of steel is 0.000012 per degree Celsius, or 12 times 10 to the negative 6 per degree Celsius. Change in length equals 10 meters times 0.000012 per degree Celsius times 50 degrees Celsius. This gives us 0.006 meters. Increasing the temperature of a 10-meter steel bar from 20 degrees Celsius to 70 degrees Celsius will increase its overall length by 6 millimeters. Example 4. A copper pipe is erected at 20 degrees Celsius and is to carry steam at a temperature of 320 degrees Celsius. How much expansion would you expect in a 30-meter straight section of this steam line? The coefficient of linear expansion of copper is 16.5 times 10 to the negative 6 meters per meter per degree Celsius, which is the same ratio as 16.5 times 10 to the negative 6 millimeters per degree Celsius. Change in length is equal to 30,000 millimeters times 0.0165 millimeters per original millimeter per degree Celsius times 300 degrees Celsius. This gives us a total linear expansion of the pipe of 148.5 millimeters. Volumetric expansion of solids. A body which expands when heated expands in all three linear directions: height, width, and length. So, heating it also expands its volume. To find the amount of volume expansion, the coefficient of linear expansion can be applied to the three dimensions of the object. Another way of saying this is the coefficient of volumetric expansion equals 3 times the coefficient of linear expansion. Expansion of liquids. With very few exceptions, water being one of them, liquids expand as they increase in temperature and contract as they cool. Unlike with solids, the rate of expansion and contraction is not directly proportional to the temperature. That is, the amount of expansion for a given liquid is different for the same amount of temperature change at different temperatures. For example, the coefficient of expansion of alcohol between 0 degrees Celsius and 10 degrees is 0.0011, but between 10 degrees and 60 degrees, it's 0.0013. Water is an exception to this rule. It contracts as temperature is removed to a temperature of 4 degrees Celsius, at which time it expands until it freezes. Transfer of heat. Heat will always flow between two objects of different temperatures until they have reached an equilibrium. The rate at which heat will flow from one object to the other depends on the following two factors: the temperature difference itself, large differences equalize faster, and the physical properties of the two bodies, that is, their specific heat and heat conductivity. Conduction. Conduction is a method of heat transfer occurring from the direct contact of a hotter object with a colder object. It is a transfer of heat energy by the movement of molecules. An example of heat conduction is placing one end of a metal rod in a fire. Soon the other end will become hot. The factors which contribute to the speed of heat transfer by conduction is temperature difference, the kind of material through which the flow takes place, the time during which heat flow occurs, the thickness of the material, and the surface area involved. The highest speed of heat transfer is between dense materials, because of the close proximity of their molecules and hence increased rate of collisions. For example, most metals are very good conductors of heat, whereas gases are very poor ones. Convection. The transfer of heat by convection involves the movement of a fluid, gas or liquid, from a heat source. As the fluid warms, it expands, causing its density to lower, and it moves up, being displaced by cooler fluid. Still air is a very poor conductor of heat. However, allowed to circulate through convection, it is an effective means of transferring heat. Most insulations, such as fiberglass and styrofoam, work by keeping small pockets of air in individual containers, keeping them from flowing and transporting heat. It is not the material of the insulation which retards the movement of heat, but the low conductive standing air in the pockets. Review questions. The amount of heat required to raise the temperature of a unit mass of a substance 1 degree Celsius without changing the state of the substance is defined as its specific heat. Blank heat is the heat that causes a change in the temperature of a substance without changing its state. Sensible heat. A bimetal thermometer consists of A. A filament that is compared to the object being measured. B. Two dissimilar metals rigidly fixed to each other. C. Two dissimilar wires connected to a battery. D. Two copper wires connected together. E. Two silver wires and a ground strap. And the answer is B. Two dissimilar metals rigidly fixed together. When the temperature of an object is raised, its increase in length is proportional to its initial length.